Hello students, this video is designed to help with Chapter 3 describing relationships. We've already done some of these pages in class, so I'm going to catch you up on some of the other pieces of information that you need in order to answer these questions. The first thing I'd like to take a look at is the least squares regression area, this area here. We're given a scatter plot and we can clearly see a trend. What we're going to do now is try to calculate the equation for the line of best fit or for the least squares regression line. Before we do that, as a quick review, remember that there are 4 different areas or 4 different aspects that you can grade a scatter plot on. You can talk about its direction. In this case, this says a positive correlation. You can talk about its form. It does appear linear, and we're going to get into how to check that form a little bit later. Its strength, these points all look like they will be pretty close to the line of best fit, the least squares regression line, so it's a fairly strong scatter plot, and also any outliers, unusual features. Doesn't look like there's any unusual features here, as we could probably figure out by graphing the line. All right, let's try to make a line of best fit. Here's your calculator, and what you're going to do is take the calculator, turn it on, obviously, and go into Stat, Edit. If some goofy guy has been using the calculator before you, you press second plus 712, which is what I'm going to do right now, second plus 712. The next thing I'm going to do is go back into that Stat Edit menu and put in all the pieces of data from this particular situation. Now that all this data is in here, I can go to Stat and then go to Calculate. Remember, in class we talked about this, we're not using linreg ax plus b. In statistics, we generally use a plus bx as our linear regression equation. And pressing enter for me, in this case, gave me negative 159.47 as my constant and 30.09 as my slope of the linear regression or the least squares regression line. Now notice that it didn't give me the correlation coefficient. In order to get that, I'm going to press second and then catalog to go to the diagnostics menu. I press D to go down to diagnostics, and the calculator says, "Are you sure you want diagnostics on?" You say yes. Stat Calc 8 should give you linear regression again, but this time it gives you the R value, that 0.958. That's a very good, very strong, positive linear correlation. R squared we're going to be talking about later on in the video. So at this point, you should be very aware of how to do least squares regression to calculate that line. Now let's talk about residuals. An important thing to remember about residuals is that they are the difference between the actual data value for y and the predicted data value for y. So for example, if I were to go back here to this situation and I were to say, well, for 14.2 degrees Celsius, they sold $215 worth of ice cream, how much do we predict that they're going to sell at that certain temperature next time? Well, what we do is use our regression equation that we found, our least squares regression equation, to make a prediction, and then see the difference between what actually happened and the prediction. So you can see I did the work here. I took the linear regression equation, the least squares regression equation, I substituted in 14.2, which was the x value, and we got 267.81. That's going to be the predicted value. So now we have an actual value, that's this, and a predicted value, that's this. Remember, residual is actual minus predicted. It says it right here. So I used my handy dandy calculator to get negative 52.81. Now that means it's a negative residual, which means that the actual value is less than the predicted value. All right. On to the partner practice. Hopefully you should be able to do this by yourselves without a partner. You're going to try this out and see if you can get it right. Pause the video and then come back when you're done. All right, hopefully you got this. I got the least squares regression line. I used that least squares regression line to find the predicted value for 77 inches tall, which was 236.96. Actual minus predicted is the residual, so I calculated the residual to be 3.04. And then predicting the height using a weight is as simple as taking the y hat and replacing it with that 185 figure. All right, moving on to the next part. We've already spoken about outliers for univariate data, but an outlier for bivariate data for a scatter plot is a little bit more difficult to quantify. So I gave these 3 pictures as an example. All right, a data value that has an extreme x value, extreme y value, or both, that would be an outlier. It's also possible that it's an outlier if it is well outside the main data cloud. If you're looking at this first example, the first example has a point that's here. You can see that its x value is very very in between or very in the middle of the other x values, these x values down here and these x values up here. However, its y value is significantly above the rest of the y values, so I would say that it has an extreme y value. Contrast that with this point. This point has an extreme x value because 1250 is much higher than all of the other x values given, whereas its y value is pretty much in the middle of the pack. So these are two examples of outliers because they have extreme x or y values. Looking at this point here, it does have an extreme y value and an extreme x value. It doesn't really matter that it is along a supposed trend line here. It doesn't really matter that it basically goes directly through that trend line. It's still considered an outlier because it lies well outside of the main data cloud. That's this cloud down here. And there are differing degrees of outliers, but in general, that's how you detect whether it's an outlier. There's a main difference between leverage and influence that I want to talk about, and the difference between leverage and influence is what exactly the point does to the rest of the scatter plot. In order to best understand leverage and influence, take a look at an example. This value here, this point on the scatter plot, has an x value that's not very extreme, but it is very outside of the trend line. It's very outside of this overall trend. So there's a big distinction to be drawn between leverage and influence. Since the x value is fairly similar to or fairly in between the other x values, I would say that it has low leverage. The trend line may look a little something like this, going through the points. If you include this outlier, it would pull that line up, but it wouldn't necessarily greatly influence the slope. However, it does have a high influence because it is outside of the data cloud. Influence is measured as far as how far away it is from the rest of the data. Leverage is really referred to as its x value. Let's contrast that with this example. In this example, the x value of this outlier is extreme, I would say. It's much larger than the other x values. So it has a different value for leverage, and it also has a different value for influence because this point, which was way far away from the trend line, whereas this isn't as far away. We could safely say that this point has high leverage because of its extreme x value. However, its influence is not that large because it's not that far away, not as far away from the trend line as this x value. Let's take a look at the third one, in which the outlier is out here. We know that this outlier has an extreme x value, and we also know that it's fairly close to the trend line, so you could probably predict what's going to happen here. A point like the one that is here has high leverage because of its x value. Whenever you think of leverage, you can think of the x value. And low influence. It doesn't really influence this trend line, this least squares regression line, because it doesn't really lie off of that line at all. In fact, the line basically passes right through it. So that's the difference between leverage and influence. Take a look at residual plots. We spoke about residual plots a little bit earlier, but I wanted to cement this difference in your mind here. This is an example of a least squares regression line, and you can see that all of the actual points are not exactly on the predicted line. This red dot here represents the predicted value for this x value, and this blue dot here represents the actual value. We can also see that this distance is going downwards. The difference between the predicted value and the actual value is negative. So if I look at my residual plot, this point represents the negative difference between the actual value and the predicted value. It matches directly up with this distance away from the regression line. So does this. It's a larger difference, so it's a larger negative residual. This is a significantly large positive difference, positive residual. As you go on, you can see that each and every one of the points corresponds to a different residual, and they're all keyed into the x values. For example, this x value is directly at 5. You see it's a negative residual. This x value, which is basically directly at 5, is a negative residual. So every one of the points that's given, you can calculate its own residual, and it's based on the x value of the original observation. Hopefully that makes sense. Now that you have a better understanding of residual plots, let's take a look at what their purpose is. Each of these are different scatter plots. You can see the scatter plots have the least squares regression line drawn in, and underneath you can see the residual plots. Here we can see that the points are basically uniformly distributed above and below the line, and the residual plot's job is to amplify that to see if there's any trend that we missed when we made our least squares regression line. Here you can see they're all very close to the line. Here you can see that they're a little bit more spread out, but they're evenly spread out, so it doesn't indicate to me that I did a bad job of predicting what the path of the line should look like. In other words, I've said this form is going to be linear, and the residual plot says, well, I can't see any other form here. It's very random, so I would say that the form is okay. It's not a very strong relationship, but the form is good. Here we can see that we started off with all the data points that are very close to the LSR line, that least squares regression line, but it's getting farther and farther away. The points are spreading out. So you can see that the residual plot looks a little bit like a cone. Still not that bad in terms of form. This example, the scatter plot here, is why we use residual plots. It looks to me like this is a pretty tight fit here when I look at the least squares regression line, but when I look at the residual plot, there is a clear pattern to it. The pattern is curved. So I would say that if I use a linear form to describe the scatter plot, I would be barking up the wrong tree. This really should be a non-linear sort of regression. And there are different types of regressions. This does look like a quadratic equation, maybe like a parabolic graph, and we're not going to be talking about parabolas in this class. All right, summarizing residuals, you should be able to do this by yourselves. Consider the sprint time and long jump distance data from page 1. We worked with this already and made a scatter plot for it. Now calculate the residuals for these data. It should be very straightforward. So pause the video, take a look and see if you can answer these questions, and then come back and see if you did it right. I calculated the first residual here. I used the LSR equation, the least squares regression equation. I substituted in 5.41 and I got 167.34. I did actual minus predicted to get 3.66. Now this does seem like a cumbersome process, but there is a way on the calculator to do it, and I will show you, even though there's a couple of different steps to remember. The first step to performing this calculation to get these residuals is to put all the information into the calculator into your stat edit menu. Once you're done with that, you can use the calculator to calculate the residuals all by itself. Your next step is to go to Stat, and then Calc, and then do number 8, which is linreg a plus bx, and it should give you the linear regression equation. The next thing you're going to do is ask the calculator, well, let me see the residuals, which I'll show you now. After you perform a linear regression, the residuals are stored in a list called Resid, R-E-S-I-D, which is short for residuals. In order to get to that list, you press second and then go list. You can see on the bottom here, it's Resid, R-E-S-I-D. So I go to number 7 and press enter. Now, this list is a very long list and it's not very easily accessible here, but I can ask the calculator to put this list into L3. Remember, I used L1 and L2 for my X and Y data. So I go store, and I want to put it into L3. So you see L3 is right here, second, L3. That way, these data are stored into the third list. Once you're done storing it into this list, you can go to Stat and edit one more time. You can notice that the third list has all of the residuals, 3.68, which I got 3.66 because of rounding error. All of these are the rest of the residuals. So if you're ever asked to calculate a bunch of residuals, don't worry, the calculator's got your back. Next, we have to talk about the difference between standard deviation and coefficient of determination of residuals. They both describe residuals, but in different ways. Now, this is the typical prediction error when using the least squares regression line. This is the formula for it, which should look a little familiar because it's very, very similar to the formula for standard deviation of a sample, except we're dividing by n-2. Welcome to the club. It answers the question, for a given LSR line, how far off is the prediction from the actual value on average? So it's a good measure of how far off your prediction is from the actual value. That's for standard deviation of residuals. Now, coefficient of determination, also known as R squared, which you've seen before in some of the other computer printouts, still uses the squared distances, just like standard deviation, but it's trying to assess the overall closeness of points of the least squares regression line. You can see this picture, and there's an example in the textbook that tells you to go to rossmanchance.com to see this applet, but it answers the question, what percent of the data's variability is accounted for by that LSR line, by the least squares regression line? So if your R squared value is, let's say, for example, 65%, that means that 65% of the variability is explained for by the least squares regression line. So the larger that number is, the better your least squares regression line is. All right, we've spoken a lot during this video about linear regression and least squares regression, but we'll have to wait for the next video to finish out this chapter. Again, we were talking about describing relationships in AP statistics. Good luck studying.